Okay, I'm going to start by giving you a little overview of the difference between discrete distributions and continuous distributions. So you've come across some discrete distributions. So a discrete distribution, the classic case of one you've come across is the binomial distribution. The key thing about the binomial distribution is that you can only have set outcomes. There are only set outcomes that you have. You either can, like 3 successes, 4 successes, 5 successes, stuff like that. You can't have 2.1 successes. If you were to flip a coin, you can't get 2.1 heads. There are a set number of outcomes. So number of heads, e.g. number of heads. Okay, so a continuous distribution is kind of like how you might think, is where you've got a set different kind of outcomes. Now what it could be anything. It could be a sliding scale of outcomes. A classic example we think of is things that you measure the length of. So a continuous distribution might be of heights, or the length of time before something breaks. The specific one which we're going to be looking at is the normal distribution, although it is important to say that there are lots of different examples of discrete and continuous distributions. E.g. heights, maybe if you were measuring wingspans, you might get that measuring wingspans of birds. It could also be time, something like that. Now, the amazing thing about the normal distribution is actually it is this set curve that looks like this that's on the screen, but actually it's amazing how many different situations have a normal distribution. It's actually the case, for example, that people's heights pretty closely follow a normal distribution. So if I took all of the measurements in the class, and actually I have done this in the past, and kind of tried to look at them, maybe with, I would probably have to create a histogram, which is not quite a continuous distribution, but you'll be able to approximate it. It would have pretty much this shape. So let's have a look and a bit of a think about this shape. So some key facts about the normal distribution. Now this is where it's kind of hard for me to do an accurate drawing on here, but it has this very recognizable shape. That is not bad. And people often call it a bell curve. It's also called a Gaussian curve after Gauss, but you can kind of think of it as a bell curve. It is symmetric. That's an important thing to know about it. It has, in the middle of the distribution, it has the mean, either, since we're going to be talking about a population, I'm going to put mu, which is the mean. And you kind of go either way with standard deviations from the mean. So you will have done outliers before. This is going to relate to it. When you talk about an outlier being more than 2 standard deviations from the mean, something you would have done before, what you're really talking about is the normal distribution. So it is true that the points of inflection on a normal distribution, where the curve changes between concave and convex, this is where, and if I go down here to the x-axis at the bottom, this point here is mu minus the standard deviation sigma, and this point here is mu plus standard deviation. And so you can kind of think of things beyond either way as outliers. And it is true that about 68% lies in between those 2 points. So about 68% of people, if it was a normal distribution, would lie 1 standard deviation from the mean. And to start to kind of to go a bit further, if I was to go one more step now, and to go to 2 standard deviations from the mean, so if I was to go to that point there, so I can go, here is mu minus 2 standard deviations, and here is mu plus 2 standard deviations, you actually get 95% lie within 2 standard deviations. Now, if that feels familiar, the idea of 95% or 5% being at each end, so 5% adding up to at each end, if that feels a bit like your binomial hypothesis testing, it really is, because if you remember in binomial hypothesis testing, you're saying the extreme results are the ones where we would reject the null hypothesis, and that's what we're saying. If you're more than 2 standard deviations from the mean, it's an extreme result and one which would suggest that maybe you might reject a null hypothesis. At the end of this chapter, there will be a hypothesis test, but we're not doing that yet. Okay, so we can start to calculate some things. So, firstly, this is the way that I would write a normal distribution. You would write, and I'm just going to be clear about that, what this is x is normally distributed. When you did the binomial distribution, you said x is binomially distributed at b. Now we're going to put in normal. We're going to put the mean here, and slightly irritatingly, we actually put the variance there, not the standard deviation. Even though we are actually always going to be talking about the standard deviation, this is the mean, and this in total is actually the variance. It's something you have to be very careful of when you're writing it down. As you can see, I might quite often write it 10, 3 squared. Because I'm immediately going to be just thinking about the standard deviation, quite often you'll see it written 3 squared. However, if that was written 9, you would need to know that actually standard deviation was 3. Okay, so we are going to now start to do a couple of calculations. Before we actually use the calculator, because we're going to use the calculator in a minute for this, you can actually do some bits on this without using the calculator. So if I had a normal distribution with a mean 10, so I'm going to put 10 is in the middle, the probability of x being greater than 10, well, that's like the probability of being above the average. It's symmetric, equal on either side, and it's going to be 0.5. Now, at this point, it's important for me to say to you, we are talking about a graph here. The thing on here that represents probability is area. In the binomial distribution, you added up the heights of all of the probabilities, whereas on a normal distribution, probability is area. So I'm going to show you that. This would be 0.5 because it's r at half of it. Probabilities are areas. Now, the next thing here, I've got this problem. And you might say, well, how are we going to calculate that? How can I work out the area? Am I going to have to do some integration? And yes, you could do integration, but it's very, very, very difficult beyond A-level integration. We're not going to bother. Before we start using the calculator, we can actually answer this question, because you might spot that what I've actually done is I've gone 1 standard deviation from the mean, because this is 10 minus 3. Do I have a red? I need a red pen. This is 10 minus 3, and this is 10 plus 3. And I just said that the probability of being within 1 standard deviation of the mean is 68%. So in this case, again, before we're using a calculator, I can actually say that this is 0.68, just because that's a common fact that we know, 1 standard deviation of the mean. And likewise, this is 10 minus 2 times the standard deviation, and this is 10 plus 2 times the standard deviation. So this is 0.95, because 95% lies within 2 standard deviations of the mean on a normal distribution. Okay, at this point, I would say that you could have a look at exercise 3A. I've talked about stuff that you would need to know for exercise 3A, and my recommended questions would be maybe questions 1 9. You don't need to spend that long on that document. Okay, I'm going to now go on to starting some calculations with the normal distribution using a calculator. Okay. So, a random variable x has normal distribution with mean 30 and standard deviation 5. So you would quite often see this written, x is normally distributed 30, 5 squared, because the standard deviation is 5, so we want a variance of 5 squared. Probably wouldn't write 25, there's not really much point. Let's leave it as 5 squared because we're just going to be using 5. Find the probability of x is less than 39. Now, it's kind of to say to you that actually these questions used to be a lot harder in the previous specification. They're a lot easier now because actually the calculator just works this out for you. There is a funny thing though. So I'm going to get a calculator up on my screen. So we want to be going to menu. And I say if you're in the room, you might want to do this along with me. I want to go to menu. And I want to go to distribution, which is where you used to do binomial distribution. And you'll see that actually you've always had them on the screen, normal distribution. My first point is forget PD. It's not going to come up. We can talk about it another time, but for me getting through the thing now, it's not going to be. It's the height of the graph, which doesn't even represent probability. It's a bit like frequency density. The most important one that we're going to use first is, well, the ones we're going to use are 2 and 3. We're going to start with 2. This is just going to tell us the probabilities. It's going to give us the probabilities. So I'm actually going to do this second one first. On the screen, I'm going to do the probability of 23 to 41. So I want to go from 23, that's the lower end, up to 41. And careful here, we often talk about mean and then standard deviation, but the calculator writes standard deviation first, so we have to be really careful to do it the right way around. Our standard deviation was 5, press equals, and our mean is 30. And now if I click equal, that's the answer. It just gives it to me. We're going to give it to 3 decimal places, 0.905. So going back to here, it is 0.905 to 3 decimal places. That's it. That is the probability. Just to kind of give you a vague idea, I do recommend, if questions get harder, just thinking about what this looks like on a little sketch. We've got a mean of 30 in the middle, and I'm going from 23, so maybe down here, up to 41, maybe somewhere up there. It's not really to scale. And I have calculated this area. I think I didn't say this explicitly, but the total area under this graph adds up to 1 because all probabilities add up to 1. The graph does actually go infinitely in most directions, but it gets very, very close to 0 as it goes in each direction. So we can see what we've just found and what the calculator has told us without using any of those facts of the graph that we were talking about is that this is 0.905 in area, the probability of being between 23 and 41. Okay, going back to that first one though, less than 39. So we go back to our calculator. I'm going to press AC and go back to this screen. There is a slightly odd thing. It would be nice if I could just say less than 39 on this calculator. The calculator is a bit weird though, and it gives us no option to turn off lower. So it has to be between two things. There's a bit of a fudge, but mathematically sound fudge. And the fudge is you put a really, really small, a really big negative number in there, and it just kind of goes far enough to give you enough accuracy on the screen. If you're not happy with it, I'm not that happy with it either, but it's what we got. So I'm going to put, because I want to go up to 39, I'm going to put minus 99999, something like that. That will be plenty, and then I want to go up to 39. So if you think of it, I've gone from minus a really, really big number up to 39. Same standard deviation, same mean, and it gives me that probability. So the answer is 0.964. 0.964. Maybe it's worth just quickly having a look. Does that make sense in terms of my graph? Yeah, it kind of does. 39's about here, and I'm going all the way down. So that feels about right when I look at this screen. Okay, this final example, probability of less than 21 or greater than 27. So I'm going to draw a quick picture. This is where it's useful to draw a quick picture. It can be fairly rough, just to kind of give you an idea of what are we talking about. So 30 is in the middle, 27 is here, 21 is here. And I want less than 21 or greater than 27. So on my graph, I want above here, I want all this bit, and I want less than this bit. So I want the total of those two parts. Now, since the total adds up to 1, with a bit of thought, I can see that this is going to be 1 minus the probability of between those two values. So I could work out the two bits separately and add them up, but it might actually be quicker for me to do it like this. So I'm going to go to my calculator. I'm going to go between 21 and 27, 21 to 27, and I'm going to get a value of there. So that bit in the middle, this bit here, is 0.238. But I want the other bit, so I guess 0.238. I could write here 1 minus 0.238. Doesn't feel that satisfying to kind of work that out. I want to kind of do 1 minus this thing on the screen, so I'm going to use the store feature on the calculator. I'm going to click store and then store it as the red A, store A, which has stored that value. Very useful in all parts of the calculator. I'm now going to go back to mode 1, just my normal calculator screen, and I'm going to do 1 minus alpha A, and that's going to do 1 minus that value, which is the answer I want, 0.762. So I can write my answer as 0.762. Okay. Just give me 1 second. Okay, that has covered up to exercise 3B as well, which I think I'm going to give it a suggestion of a couple of questions and then pause this video for now. So at this point, you should be able to do questions from exercise 3B. And I recommend, if you wanted to just do a couple, doing questions 1, 4, and 7, as well as reading the examples. And I've got a page, it's page 43 in the Year 2 Applied Pearson textbook. So that's page 43. Okay, I'm going to stop this video now